Yeah, I'm Zander, and I'm excited to be here today to talk to you about real-time revolution. So we're going to talk about real-time data and streaming data. So as you probably know, it's hard to not interact with data in real time. It's all around us today. That can be from social media interactions or to the stock market. Or maybe it's a manufacturing facility where practically everything is automated and generating millions of data points. Or it's your car, which unknowingly or knowingly can generate up to 25 gigabytes of data an hour. Or maybe it's the device in your pocket that is tracking you as you go through your day-to-day life. Now, companies, many of those that are leading and beating out the competition, take advantage of real-time data. And they do this in many different ways. And some of the most common are recommendations, like the social media applications we saw, advertisements all across your favorite platforms, personalization when you're doing your Christmas shopping or whatever it might be. And then some nice use cases like fraud detection that can protect you from being taken advantage of for your PII or your credit cards. Before we go any further, I want to introduce myself a little bit about who I am, why I'm here. I kind of think it tends to make things a little more personal. So I'm Zander, and I'm currently working on Bytewax. Before that, I worked on data infrastructure, machine learning infrastructure, and data science at developer tools and developer platform companies like GitHub and Heroku. When I'm not working on Bytewax right now, I am also a proud human and dog dad. That's my daughter Zaya and dog Kika. I bring them into many of my presentations. My daughter's just slightly younger than this startup, and so you can imagine it's a fun time if you've had kids. This is the other thing I like to do outside of work, which is getting outdoors. And this is me hiking up Tuckerman's Ravine. If you've ever been there, it's Mount Washington in New Hampshire. It's one of the windiest places on earth, and we got lucky that this day it was no wind, and it was the middle of February, so we had good snow and good times and no wind. These days, you can find me hanging out in the Bytewax Slack, or you can find me in Santa Cruz, where I live with my family. Feel free to send me a LinkedIn if you're there, and we can grab a coffee. So let's get on with it. Today's agenda, we're going to go through what is real-time data, then we'll talk about streaming data, provide a little introduction. Some of this is a little high level, so depending on where your familiarity is with streaming data, you might feel like it's a little boring, but we'll get to the fun parts in a bit after that. We'll then kind of dive into what are the hard parts of streaming data, like why isn't it adopted more readily? And then we'll talk about how Bytewax, what Bytewax is, the software that we built. It's a stateful stream processor, so no surprises there. But we'll talk about what it makes easier with respect to streaming. Okay, so very, very high level, what is real time? Definition that can be used for real time is anything that is perceived to happen in real time by a human, which is a very fuzzy, loose definition, but we can kind of generalize it in the sub-second realm. And it will depend on the direct application. The stock market real time might be different than, say, a user interaction on a website. Now, in the world of data, what does real time mean? Specifically, it means that the data is made available for use as soon as it is generated. The data is then processed immediately, and the data is made available to the consumer post-processing. And so all of those steps that are involved in facilitating that need to happen in a real-time, low-latency manner. So that's what real-time data is. So what then is streaming data? Specifically, streaming data is actually just a capability or technology enablement that allows you to work with data in real time. And when I describe what streaming data is, I like to do it in contrast to batch because it gives a good comparison on the differences and helps to understand. So we can start first with the data itself. Streaming data is a continuously generated and unbounded data, whereas batch is a bounded and known set of data. And because of the nuances of working with the different data, specifically the unboundedness, we react to them and process them in different ways using stream processors or batch processors. And each of those leads to this paradigm of batch processing versus stream processing. Stream processing paradigm, we process things one at a time as they arrive, whereas batch processing will batch that entire known set of bounded data. And as you can probably imagine, there are difficulties and different things that arise when you're doing either of those. Today, we're going to focus obviously on stream processing. This is a little bit about what stream processing is. So I'm going to do a little experiment next. And I like to do this. It's kind of like, I don't know, fun for me. But I use Python generators to kind of explain what streaming data is. It gives like a pretty concrete example. So we've got a little notebook here. If you're not familiar with what a generator is in Python, it's an iterable object or somewhat iterable object where you can kind of request what is next and it will yield it forward. And it has different use cases within the Python community. So what we're doing here is we're simulating a stream of data with a generator essentially. So we create a function. It's basically an endless while loop. And in that while loop, we're just going to generate a random number. And we're going to yield that back. So that's the sort of like generator part that we're creating there. And so you can imagine this is a stream of sensor data where the sensor is throwing off some information and we're going to be collecting that downstream. So we have this fake stream of data. And the next part to understand about streaming, so streaming data is like, so you have this stream, this continuously generated unbounded set of data, and then you have this idea of how do you consume that stream. And so there's a bunch of techniques and software that allows you to consume streaming data, and we're going to make a consumer here. So the consumer in this setup we have is just going to be a handle on our generator. So we're creating that object here, and then what a consumer does with a stream of data, although it may feel like the data is being constantly pushed to the consumer, the reality is normally it's that the consumer is actually requesting eagerly what is the next available data. And so in Python, you can kind of, I guess I should run all these. In Python, you can simulate this by just calling the next item of the iterator, which is going to give us the next random available integer. And so it was interesting that was the same number that time. But so anyway, that simulates how the consumer works, where we're just requesting, hey, what's next? Hey, what's next? Hey, what's next? So if you've ever used Kafka before and you've used like the Python Kafka library or the Confluent Kafka library, what's happening under the hood is you're actually like polling Kafka saying, hey, what's next? What's next? And then the Kafka system will provide you with like the next available data in that stream. So how do we process this data? We have a consumer and now we need to process it. And so it can be as simple as like, hey, for every single data point that you get, I just want you to divide it in half. And so we can do that. And we can loop through this to simulate a stream of 10 numbers. And then we're dividing that number in half and just taking a pause. Okay. Checking out if there were any questions. So it's pretty straightforward. Like, I mean, it's almost an overly simplistic example. So like, what if you had many of these values at a time and we wanted to actually do something where we're incrementally updating some analytics so that we can make a decision downstream. And so we can simulate that here too. And we can basically say every two values, I want to take the average of them. And then I want to pass that downstream. Once again, it's quite overly simplified, but it's a good example of what we would do next in an actual use case. So like okay, we've been able to connect to this stream and we can request the data and we can see it. Second, okay, we want to do something to that data. And third, we want to get a little more advanced with what we're doing so we can use that data for some other system downstream or like broader operational automation. So you might be thinking to yourself now, well, that seems super simple. Like, why do we actually need a stream processor? But it really gets quite complicated quickly. And so that's why people have worked on building systems like Apache Flink or Spark structured streaming and Bytewax. So the next part of the talk, we're going to talk about these difficulties, and I'm going to specifically tie them back to how Bytewax can be used to overcome some of these difficulties. So the first thing, when we're going through our sensor data, we were pretending it was just like one sensor, but in the reality, we might have many different sensors. And so each sensor will have its unique ID, and then it becomes quite complex to manage all of that data for all of those different sensors for whatever computation we're doing. In the next case, what happens if we actually wanted to do our average that we did in that second part of the example, or the last part of the example, I should say, from the Google Colab notebook? What if we wanted a time-based window? We could do a time-based average. And then you could think about like, oh, what if data actually arrived late? How would it fit in the window? Or what if we had multiple inputs and we wanted to join those inputs together? Or which oftentimes happens, something fails for one reason or another. And what would happen if we lost track of where we were in the stream of data, especially if we were sort of had this larger window and we were accumulating some state or calculating some number? How do we go back to the right spot in the stream so that we know exactly what the calculation was, and then we can start to build on that again? So you can imagine how complex things can really get, especially if we're writing this like just with Python and generators and kind of doing it all on our own. And then finally, what if we need to scale things up? So at some point, we have so many sensors. We've expanded our proof of concept into many different warehouses or wherever the sensors live, and we need more processing power. So how do we scale that up? And how do we increase the number of workers so that we can actually process our data within the requirements of latency that we have? And this can become kind of difficult because let's think back to the key situation. So we had all these different keys and we're doing this calculation with those keys, whatever it is, a running average or something like that. So how do we ensure that the right key gets to the right worker so that our calculations are correct? And then if you add in, okay, now does the right key get to the right worker? And then when things fail, where do I resume? There's all sorts of things that are gotchas. And that's why stream processing has inherently been so complicated, and the systems to use it have been quite complex. So at this point, I want to introduce Bytewax. What's kind of fun about this talk that I'm giving is, well, for me at least, I don't know if you all are familiar with Bytewax. If you aren't, that's fine. If you are, I'm going to introduce some new syntax and some new capabilities that's being released in the library in 0.18. And I'll maybe expand a little bit at the end of this on kind of like what's on the roadmap for Bytewax in the future. But so Bytewax, for those of you who don't know or have not used it, it's a open source Python stream processor. The project is a little under 2 years old, and we've spent the last few years building out the features we thought were required for a production-ready system. And so we are pretty well on our way to having Bytewax be production-ready for many, many, many use cases. So first, it's a Python native API. You might be asking yourself, like, why did you do it in Python? And the reason we built it in Python, part of my background is in machine learning infrastructure. And one really hard problem that we could never really solve well at GitHub was that, where I worked in the past, was how do we compute features in real time so that we can make online inference? And computing features in real time required us to take what we did in training jobs to train the model and do that all in real time. And so the code that we used for that training job wasn't necessarily reusable if we were going to use the existing systems, which were Flink or Spark structured streaming, where you don't quite have the same capabilities of Python dependencies or even have just the capabilities to do what you wanted to do. And so that's why it's a Python native API. So you can leverage the entire Python ecosystem when you're working with streaming data. It's built on top of a project called Timely Dataflow. Timely Dataflow is a Rust crate that you could use directly for processing data. It's a data parallel processing engine. It's the same processing engine that powers Materialize, if you're familiar with the streaming database. We built on top of Timely many of the production requirements that we thought were necessary, like the rescaling, so you can increase or decrease your workers, state persistence, connectors, etc. Bytewax is stateful, so you can do all of those hard things we mentioned. It's cloud native. So one other thing we thought would be useful when we were thinking about how we could introduce a Python stream processor was, why don't we take advantage of the systems that exist today that maybe didn't exist when when things like Spark and Flink were made in the past. And so we leverage Kubernetes pretty extensively when you go to scale Bytewax or use the platform, which we've built a bunch of production and operational features into. So that's the long of what Bytewax is. And if I still have you and haven't lost you yet, we're going to go into some of what the code looks like. I tried to make this kind of holiday themey, but yeah, it looks a little gross. But yeah, this is the holiday theme that I could get from carbon.sh. Quick question on the chat right now: are you working with vector DBs already? So I'll take a step back for 1 second. So Bytewax is a framework and processing engine, and the framework gives you semantics to describe how you can connect to, process, and then write out to different data, connect the data sources, process data, and write out to different data sinks. And so you can use Bytewax with anything that has a Python client. There are obviously some gotchas there because you need to be able to track progress on the data source so that you can recover. So I'm trying to answer this question, but I don't know. Anyway, so the question was, are you working with vector DBs already? And the answer to that is you can use Bytewax with vector DBs. I have written a bunch of blog posts and some examples of how you can use Bytewax to create embeddings and store them in a vector database like Redis or Quadrant or whatever there is a Python client too. Okay, so moving back to our hard gnarly problems of stream processing. There's one more question, and I'll answer it in a second because it's going to be answered in the next slide or two. So what if our input had many different keys? This is a very common problem. You're scaling up your system. You have many different inputs, many different pieces generating data, whether it's there's users generating data or sensors or whatever it is. So here's an example of how you would connect to Kafka with Bytewax. So Bytewax has a concept of a data flow. That's essentially like the workload because you describe the processing steps in a data flow, which is a programming paradigm where all the nodes are all the steps are like a node in the graph. So you define a stream as the first thing, and that's used an operator to say your input, and then you can provide it with a connector, which is the Kafka connector, and there are some built-in connectors, but you can write your own. You can parse the data, and then that's just with a simple map step, and then you can use a different operator to kind of extract the key, and then we'd be able to use that downstream when we're doing reduce or window functions or joins. So each step in the data flow uses an operator, and inside the operator, you pass it Python code. That's basically how it works. So what if we need a time-based window? That was one of our other hard gnarly problems. So this is how you would do a window in Bytewax. You can either use system time or event time. If you use event time, you pass it a Python function on how to pull out the event time from the payload. And then you can also define how you work with late arriving data. Once again, operators, you're passing them Python functions. So for each new key, a new window, we are telling this, we're telling Bytewax to make a list. And then for every additional value for the key in that window, we're going to run this accumulation, and we're just really appending to a list here. But you could do whatever you want. You could calculate the average directly right there. So what happens if this system fails? I'll just talk to this quickly because the question was, what is the underlying database for storing state? So we actually use SQLite on each worker for storing state, and it's backed up at an interval you can set, and I'll show that in a second. So any stateful steps or progress that's being tracked is going to be stored in that underlying SQLite database. And that can be backed up to S3 for disaster recovery purposes or migration or things like that. So I'll show you how that's done in a second. Before that, we'll talk about a new cool function in Bytewax, functionality in Bytewax, joining multiple input sources together. So we call these nonlinear data flows. You can do streaming joins, running joins, different types of joins. And the idea is you could have a Kafka topic and you could have a database. You can have two streaming topics. You can join almost anything, any different system together. So there's like really some awesome things you can do. And this is the syntax here. So you define the different input streams. So you have stream 1 and stream 2 and stream 3, and then you can, we're doing a split here. So you're splitting by a key, and then you can join all of these together. Here we're joining, and this is not a running join, so that's the other capability. So in this join, you'll wait for all the pieces to be there before you move on. So for each key, you need one piece of data. Okay, so this talks to state. Looks like I actually missing one line here, but that's fine. And scaling. So this is just how you would run Bytewax. So Bytewax, you just run it like a Python, like regular Python. Like if you were running Flask or even Fast API, I think is the same syntax. So it's Bytewax run and then the data flow object flow. And then you can run Bytewax with worker threads and processes. We'll get into the nuance between those right now. Now, speaking towards state and recovery. So when you're using recovery with SQLite, they're stored in a directory. So you create those directories, and then you just run your data flow with the recovery partitions. The recovery is partitioned. You don't need to have the same number of partitions as you do workers. They'll sort that out themselves, but that allows you to scale the workers independently of the state. This is talking to scaling again. So like I said, workers, processes, you can run Bytewax on one machine with many processes, or you can run it on multiple machines manually, or you can use our tool that we built, Wax Control, in order to deploy it on top of Kubernetes. And that's sort of the recommended production use case for Bytewax.